So let us welcome the last lecture of this course MAT-201, that is integral calculus. So in this lecture we will see the Stokes theorem and Green's theorem and examples on these theorems. So first theorem, that is Stokes theorem. Statement of Stokes theorem. So let F be any continuously differentiable vector point function and S is a surface bounded by a curve C. Then on the line integral F bar or dr bar over the curve C is equal to the surface integral curl of F bar dot n cap ds over the surface here. So Stokes theorem gives us the line integral in terms of surface integral, or you can transform line integral to surface integral or surface integral to line integral. So previously in Gauss divergence theorem we have seen we can transform a surface integral to volume integral or volume integral to a surface integral, that is integral transformation. So here where the unit normal vector n cap at any point of surface S is drawn in the sense in which a right-handed screw would move when rotated in the sense of description of C. So this is the direction of this unit normal vector n cap. So next, what is the Cartesian representation of this Stokes theorem? So we have the statement of Stokes theorem, that is line integral f bar dot dr bar equal to surface integral of curl of f bar dot n cap ds over surface S. So here let f bar is equal to suppose f1 I bar plus f2 j bar plus f3 k bar. So therefore you get the curl of f bar using definition of curl. It will be determinant of I bar j bar k bar dou by dou x dou by dou y dou by dou z, and last row that is f1 f2 f3. So if you simplify it, so you'll get I bar in the bracket dou f3 by dou y minus dou f2 by dou z plus j bar in the bracket dou f1 by dou z minus dou f3 by dou x plus k bar in the bracket dou f2 by dou x minus dou f1 by dou y. Also here r bar, so it is position vector, so it is equal to xi bar plus yj bar plus zk bar, so that so dr bar will be dxi bar plus dyj bar plus dzk bar, and n cap ds will be dy dz I bar plus dz dxj bar plus dx dy k bar. Hence, this line integral over curve C of f bar dot dr bar will be equal to. So here we are putting value of f bar dot dr bar. So that is a line integral over curve C of f1 dx plus f2 dy plus f3 dz, and that is equal to, so surface integral over S of curl f bar dot n cap ds. So we are putting here value of curl of f bar and n cap ds. So that will imply, so this dot product, so it will be double integral, means it is surface integral over S of dou f3 by dou y minus dou f2 by dou z divide dz plus dou f1 by dou z minus dou f3 by dou x dz dx plus dou f2 by dou x minus dou f1 by dou y dx dy. So this is the required form of Stokes theorem in the Cartesian form. So next, this is statement of Green's theorem. Also, this theorem is called Stokes theorem in the plane. So statement of Green's theorem is that let S be a surface bounded by a regular closed curve C in the xy plane. Let f1 xy and f2 xy be continuously differentiable functions inside and on C. Then the surface integral over S of dou f2 by dou x minus dou f1 by dou y dy dx is given by the line integral f1 dx plus f2 dy over C. So this is the statement of Green's theorem, or in particular it is Stokes theorem in the plane, means two dimension. So original Stokes theorem is in 3 dimension. So in particular Green's theorem is a particular case of Stokes theorem in 2 dimension. It is 2 dimension case of Stokes theorem. Yeah. So next we will solve some examples on these theorems. First we will solve illustrate examples on Stokes theorem. Question is that verify Stokes theorem for, so f bar is given, that is x square plus y square I bar minus 2xy j bar taken round the rectangle bounded by, so x equal to plus minus a, y equal to 0, and y equal to b. So x varies from minus a to a, y varies from 0 to b, 0 to b. So it is given. So here curve it is given, and it is a rectangle bounded by these lines x equal to minus a, x equal to a, y equal to 0, and y equal to b. And a bar is given. It is vector valued function. So you have to verify Stokes theorem. So first we will find. So you can refer this figure. So already details are given in example. So let ABCD be a rectangle as shown in the figure. So this is rectangle ABCD. So A, B, C, D. The coordinates of A are A0, coordinates of B are AB, coordinates of C are minus AB, and coordinates of point D are minus A0. So clearly it is shown in figure. So we first evaluate the surface integral, that is surface integral or yes of curl of f bar dot n cap ds. So taken over the rectangle ABCD. So here, yeah, surface is rectangle. So first we will find the curl of f bar. So using definition of curl of f bar, it is not nothing but del cross f bar, and it will be determinant of I bar, j bar, k bar, dou by dou x, dou by dou y, dou by dou z. It will be x square plus y square minus 2xy. And here, uh, so 0 k bar is there in f bar, so that will be 0. Yeah. So after evaluating the value of this determinant, so you'll get curl of f bar is equal to minus 4 by k bar. So in the present case, here n cap is equal to k bar, because so k component is 0, means here the direction of n cap will be along z axis, which is perpendicular to both x and y axis. So here n cap is k bar. So we'll use yes, we'll find this integral, that is integral surface integral curl of f bar dot n cap ds. So it will be, so x varies from, it is double integral. So x varies from minus a to a, y varies from 0 to b. Curl of f bar, that is minus 4y, and n cap ds, that is dx dy. So we solve this double integral. So first, yeah, solve a second integral, that is integration from 0 to b of minus 4, which is outside of integration, and integration of y dy. So putting limits of integration with respect to y, so you get it as b square point 2, and integration of dx from minus a to a, that is just 2a. So the resulting value of this integral is equal to minus 4 ab square. So this is using directly from definition of this surface integral. Yeah. So now let us evaluate. So next we evaluate the line integral, and we'll check whether these two integrals are equal or not. If equal, then that will be verification of Stokes theorem. So now let us evaluate the line integral along the curve C1, C2, C3, and C4. So already we have denoted it in figure. So which curve is C1? Yeah, AB, that is C1, B to C, that is C2, C to D, that is C3, and D to A, that is C4. That is four edges of this rectangle. So we are taking curves C1, C2, C3, and C4. So I1, that is line integral over C1, I2, that is line integral over C2, and likewise I3 and I4. So first we will find the line integral, that is I1. So line integral I1, it is line integral over first curve C1. So along C1 you can check. So what is C1? Yeah. So along C1, so here you can check x is equal to a, means x is constant, and therefore dx will be 0, and y varies from 0 to b. See, so x is a, and which is constant, so therefore dx will be 0, and y varies from 0 to b. So this integral will be yeah, x square plus y square dx minus 2xy dy, and here dx is 0, therefore this term will be 0, and it just, and we are putting x equal to a because x is a, x equal to a along c1. So this integral will be minus 2ay dy, or you can take minus 2a outside, and this integral will be y square upon 2. After putting limits, it will be b square upon 2. So After simplification, you will get the value of I1, that is minus AB square. Similarly, I2, that is a line integral along curve C2. So along curve C2, you can observe y equal to b, which is constant, and therefore dy equal to 0. So second term in this integral will be 0. So simply integral will be a to minus a x square plus b square dx, because we are putting y equal to b along C2, and this integral will be, so after simplification, it will be minus 2 upon a is a cube minus 2ab square. So similarly, I3, that is a line integral along C3. So along C3, you can check x equal to minus a, which is constant, and therefore dx will be 0. So after dx is 0 means first term will be 0, and in second term you have to put x equal to minus a. So therefore, resulting integral will be, and b varies. Y varies from b to 0. So this 2a will be outside of integral, and after evaluating, the value of this integral will be minus ab square. So last integral, that is I4. So it is line integral along curve C4, and along C4 you can observe. So y is 0, means dy will be 0, and again y will be 0. So let us put this value. Second term will be 0, and resulting integral. So in resulting integral, x varies from minus a to a. So along C4, x varies from minus a to a. So this will be the integral minus a to a of x square dx. So after simplification, finding integral, and after putting in upper and lower limits and simplifying, after simplifying, so you'll get the value of this integral as 2.3 a cubes. So now, what is the resulting integral? A line integral along the rectangle. So yeah, resulting line integral on rectangle will be addition of these four integrals, that is integral along C1, integral along C2, integral along C3, and integral along C4. So adding all these four integrals, you will get the value of this integral as minus 4ab square. So you can call this equation as equation 2. So from 1 and 2, so we can find the value of line integral and value of surface integral. So both these values are equal to minus 4ab square, and hence Stokes theorem is verified. So again, there is one example, so which you can solve as a homework. So this is verification of Stokes theorem. So again, I have written this note, that is Stokes theorem is the in the plane is also called Green's theorem in the plane. Already I have mentioned this. So next theorem, there is one theorem. If phi and psi are two continuously differentiable scalar point functions such that del phi and del psi are also continuously differentiable, then volume integral of phi del square psi minus psi del square phi dv over the region V is equal to, actually it is volume integral, so it is equal to surface integral phi del psi minus psi del phi over the surface S dot n cap ds. So here V is the region enclosed by the surface S. So next we will see example on Green's theorem. So example is that evaluate by Green's theorem in the plane the line integral x square minus cos hy dx plus y plus sin x dy, where C is the rectangle with vertices 0 0 pi 0 pi 1 and 0 1. Yeah, the path of so basically you can observe the path of portion of C in the rectangle OABC as shown in the figure. So already drawn this figure. So you can see, so this is OABC. So this is the path of this curve, and you can observe it is nothing but rectangle. So what are the coordinates of this point? So it will be 0 5. So O, that is 0 0, A, that is pi 0, B, that is pi 1, and sorry, it will be 0 1. So this distance is pi, this distance is 1, and again this distance is pi. Yeah. path of the portion of C in the rectangle OAB as shown in the figure, and you can observe it is a rectangle. So let R be the plane region bounded by C. So this is plane region. Yeah. So it will be plane region bounded by this rectangle across C. So using Green's theorem in plane, we have the line integral x square minus cos hy dx plus y plus sin x dy is equal to surface integral, and it will be surface integral over R dou by dou x y plus sin x minus dou by dou y x square cos hy dx dy. So you can evaluate this double integral. So here x varies from 0 to pi and y varies from 0 to 1. So you can observe in figure, it will be cos x sin hy dx dy. So after simplification, you will get the value of this integral pi cos h1 minus pi, that is pi into cos h1 minus 1. So this will be the resulting value of this integral, and we find this value using Green's theorem. So again, there is one example on Green's theorem. So you can solve this example as homework, and this is the end of this topic, that is Stokes theorem and Green's theorem. And also it concludes the chapter number 7, that is integral transformation, and this course, that is MAT-201 integral calculus. So I will stop here.